Yeah, hi Year 12. This is our first chapter as we dive into Mathematics Extension 1 in the Year 12 course, and it is Chapter 2 in the textbook. So what we're looking at is mathematical induction, and it's a process of solving or proving, a general theorem by examining individual cases. It's based on the premise that you can show that it is true for n equals 1. Then we assume it's true for n equals k. We prove it again true for n equals k plus 1, and therefore it's going to be true for all values of n after that. There's kind of a little script that we have to write each time we prove something, and if we follow that script and do this exactly the same way every time, it generally will fall out. We're just going to have a look at some simple ones. It'll be the first part of Chapter 2, it'll be 2a, and we won't be looking at divisibility or inequalities today. Just looking at straightforward ones. So let's follow through and see the first example here. What we're doing is proving that 1 cubed plus 2 cubed plus all the way up to n cubed, so that's a sum, is equal to n squared on 4 times n plus 1 squared for all values of n. And it's going to be saying, let's prove this by mathematical induction. So step 1 is to show that it's true for n equals 1. So we want to look at the left-hand side and the right-hand side. So I'm going to start in this case with the right-hand side. And the right-hand side for n equals 1 is going to become 1 squared over 4 times 1 plus 1 squared, which is 1/4 times 1 plus 1 is 2, 2 times 2 is 4, 1/4 times 4, which is equal to 1, which is actually equal to the left-hand side, which would be our 1 cubed, or if you think of it over here, we're popping our 1 in that n there, 1 cubed, which is 1. So we've shown that it's true for n equals 1. Now we need to assume that it's true for n equals k. So all we're doing in this section is writing a question down. I'm just going to be changing my n to my k. Now, when you are doing a proof like this, you need to be writing out in your proof these steps. So I would actually write as my next step the words assume true for n equals k. So I've done that. I've changed my n to my k. And now that I've done that, I would also write prove true for n equals k plus 1. So you're not going to get given these little sections. You need to write these in. So let's write this now down for k plus 1. So I'm going to still have my k cubed, but I'm going to have a next term, which is k plus 1 cubed. That's my left-hand side. My right-hand side becomes k plus 1 squared all over 4, and I get k plus 1 squared. So where there was a k in here, I pop in k plus 1. There's already a plus 1, so I'm going to end up with a plus 2 in that bracket. So I'll just fix that up. I've got k plus 1 squared all over 4. K plus 2 squared. So what I'm proving is that this left-hand side here is equal to this right-hand side. Okay, so we're going to start with the left-hand side. And what you'll notice on the left-hand side, I've got written up here, I've got that my 1 cubed plus 2 cubed plus 3 cubed all the way up to k cubed. So this section here, all up to there, I have an answer for up above where I've assumed it's true for n equals k. And that's that part there. So those pair are actually equal. So I can, and I need to pop that into my proof. And let's look at that. So my left-hand side is going to be now k squared on 4, k plus 1 squared. That's my blue part up to here. Plus, I've still got k plus 1 cubed. Now what I need to do is manipulate this algebra here to become this part here. So I'm going to need to look at what I need to do. We've got a plus in here, I don't here, so I need to factorize out some terms. So what's common to both? I've got a k plus 1 all squared is common to both. So pulling out that k plus 1 squared there gives me that k plus 1 squared there, but I need to know there's a 4 here and there's a 4 here, but that 4 only belongs to the first bracket, so I am going to need to deal with that 4 in a minute. Let's not do that yet. Let's just see what we end up with. In this case, I'm going to end up with k squared on 4 plus, and my factorised add a k plus 1 squared here, I've still got a k plus 1 left. So what I'm going to do with this second bracket here is I'm going to pop it over a common denominator of 4. So I'll leave my k plus 1 squared. If I pop all of this over 4, I'm going to end up with k squared plus 4k plus 1. And now I can pull out that 4 out the front and end up with 1/4 of k plus 1 squared. And now I need to factorise my brackets here and see what I end up with. And that should be a 4, sorry, up there. Okay, so if I factorise those brackets, I'm looking for numbers that are going to add to 4 and multiply to 4. So that's going to be 2 times 2 is 4, 2 plus 2 is 4. That's a plus 2 and a plus 2, which I'll just pop that over here, which gives me what I want. K plus 1 squared, and I've got k plus 2 twice, which is my right-hand side. So I've proved that it's true for k plus 1. Now that's not where it ends. You always need to have a little statement at the bottom, and I like this one here. So therefore, true for n equals 1, n equals k, and n equals k plus 1. Therefore, I'll put a little therefore, true for all values of n. So we need to finish it off. So that's the script that you would do for mathematical induction, looking at all of those 3 steps, 1, 2, and 3, and then a concluding statement at the bottom. Now, the multiples we'll have a look at next time. I suggest you go and have a look through the OneNote. There's a lot of worked examples in there to start working through, and we'll work on these in class as well.